So in the pre-lecture, we talked about an unbiased learner, right? The idea that you might try to think about a learner that doesn't make any assumptions about what's possible to learn. In fact, what we showed was that if we do that, we have no leverage to generalize to unseen examples. We have to memorize everything. And so it's not a feasible idea to have an unbiased learner. We always have to make some a priori assumptions about the type of hypothesis that we want to, the type of concept that we want to represent. Okay, so again, our intuition there was to show that if we choose a hypothesis set that can express every teachable concept, then we're going to have some difficulties, right? So for example, if H is the power set of all particular instances, then there's going to be a very, very large space to choose from of target concepts. Again, to recap this to make sure, if we have 6 Boolean attributes, this means we'll have 2 to the 6 possible data items, right? This is going to be our size of our script X, right? Because for each of these Boolean attributes, I can set it one way or another way and generate 2 to the 6 different items, right? So that doesn't sound too bad. 2 to the 6 is not a large number, but when we talk about how many concepts are out there for these 2 to 6 data items, it becomes much worse, because for each of these 2 to the 6 rows of data that we have, this is our total X space, which is going to be 2 to the 6 large, I can set either one of these to a positive or negative, a positive or negative, or a positive or negative, right? And this means there's going to be 2 to the power set, of the concept, amount of space of our data items, right? So it's going to be 2 to the 2 to the 6 here, right? Which is an enormous number, right? So that's going to be the case when we consider this script H prime, which is basically allowing all of the different types of hypotheses that we could do, right? Let's say we expose this particular, any particular learner that can learn this space to the example data, right? So if we take a version space, a candidate elimination algorithm that can express this very general teachable concept space, then what are we going to have for our most specific and most general boundaries? Well, let's think about it a second here. If I want to say the most specific boundary, that means I'm only going to accept the drinks that I know are positive. Well, that's pretty easy to compute here, right? I only have 3 drinks here that are positive. So I can write those as part of the most specific set, right? So it's going to be the case where I have X1 or X2 or X3, right? And that's our most specific case, right? Only when I see those 3 drinks will I accept it as positive, right? And our general set is basically going to accept everything except for anything we know is a negative example, right? So that's these 2 here. So I can write that as well. I can say for anything that's X4 or X5, right? I can write that as not being accepted, right? So what about the remaining, all of the other possible input values, right? Anything that we draw from our power set X that's not one of these 5 examples, well, then what would it classify? Well, the problem here is that in our version space, between the boundaries of S and G, there's going to be one hypothesis that accepts that drink and one hypothesis that doesn't accept that drink, that will return a negative value. So it's always going to be equally balanced in both directions. And this means that basically this type of learner is not going to help us generalize at all. We're going to need training examples for every possible instance in order to converge to the target concept. And that basically means memorizing the entire data set, right? Not helpful, because basically it doesn't allow us to classify any new unobserved training instances. We basically cannot generalize beyond the the observed examples that we've been given. So we introduced this idea of needing something called inductive bias, right? So if we are given a concept learning algorithm, an input space, and an unknown target concept, and we're given the lens of the data set, which is noise-free in this case, of having M examples to classify or learn from, then let's say that the algorithm actually returns this classification after learning all of these, and is able to return some type of classification on any new input instance, meaning new testing instances that we want to infer the values of, right? We're going to say the inductive bias of the algorithm is any set of minimal number of assertions, B, that's going to help us make that inference, right? That for any X that's in our input space, okay, that taking the assumptions with the data set and the test instance is going to allow us to arrive at the target value for that particular input instance. So with this definition of inductive bias as the set of assumptions B that we need, we can understand the inductive bias of several different algorithms. So let's take a look at the candidate elimination algorithm. We're going to show that the assumption that it makes is basically that the target function must be inside of the hypothesis set, right? So this is the case in which, for example, we assume that the target concept actually is a conjunctive hypothesis for the cases that we've been showing for candidate elimination. Okay, so we're going to make this assumption, all right? We're going to assume that the candidate elimination algorithm does actually produce a classification only when all of the hypotheses in the version space decide to either all accept or all reject that particular instance. That means everything in the version space classifies the same way. So it wouldn't cover that fourth case that we saw in the earlier part of the properties of candidate elimination, where we had to use a majority voting in order to determine an outcome. Okay? So if this is the case, and we have like in testing instance 1 and 2 from that section, then we can say that if the target function is actually in the hypothesis space, then it's also going to be in our version space, right? Because all of our target concept is consistent with the data set that we have because of the noise-free examples. Okay, so our second step in our proof is basically to show that if our learner is able to output a classification, then our hypothesis must also agree for all of them because of our assumption, right? We said that if an input instance votes a particular direction in a unanimous fashion, it is going to have this property. Otherwise, it's not going to output any type of classification otherwise, okay? So if we say that this particular instance satisfies this assumption, then it is going to be able to be in the target concept, okay, that we can find this. So this means the inductive bias of the candidate elimination algorithm is very simple. It just assumes that the target concept is actually within our hypothesis space. So like we just said, those set of B's help us to decide what type of inductive bias all of the different learners that we will learn have, okay? We're only going to study it for these toy examples, but you can generalize this in many ways, okay? This is a very good concept to remember. So in the case where we have a rote learner, which is storing all of the examples and classifying the input instances only if it matches something in the training data. There is no inductive bias, right? But the problem here is we can't generalize, right? We saw that if we're exposed in a rote learner case to any input instance, a test instance, that doesn't match anything in the training data, it's basically not going to be able to say anything about it because it's not seen it before. This is why we call it a rote learner. It's just going to spit back basically the classification from before. You can think of that like a dictionary or a hash table. In our candidate elimination algorithm that we've looked at in this post lecture, you can see the inductive bias is one where we assume that the target function is inside of the hypothesis space. For find us, as we introduced in the previous part in the pre-lecture, it is also having this assumption, okay? But it additionally assumes that all instances are going to be negative unless the opposite is entailed by its knowledge, okay? So it's going to make this very strong assumption that anything else it hasn't seen that isn't in its hypothesis set is going to be negative. So it has a stronger inductive bias than candidate elimination. So it will be able to generalize more, but have this risk of assuming that everything has to have a negative outcome unless otherwise